Hello and welcome. In this tutorial, we will learn about NumPy and CuPy libraries in Python, so let's get started. NumPy is one of the most important libraries that helps perform scientific computation in Python. This library saves data in multidimensional arrays such as 1D array, 2D array, 3D array, or more. This library performs fast computations such as mathematical operations, data shape manipulation, logical operations, linear algebra, basic statistics, and much more. Now, why don't just represent each array in Python as a list sequence? There are many benefits of using NumPy arrays over Python list to store data. NumPy data consumes less memory. Also, operations done in NumPy are way faster as compared to lists. Furthermore, NumPy has more built-in functions for mathematical operations as compared to lists methods. To start off, you can create a NumPy array using the array function. This function takes an array-like sequence such as a list and converts it to a NumPy array. In this case, we are converting a list of 4, 5, and 6 to NumPy array. This is called a one-dimensional array. You can also create a two-dimensional array by using a list of lists. In this case, we created two lists as a list of lists and converted it to an array using the array function. Notice the output result has two rows of arrays, so it is a two-dimensional array. Now, NumPy allows you to check for the shape and dimensionality of an array using the shape and ndim methods. The shape of an array returns a tuple of the number of elements along the axis of the array. In this case, a one-dimensional array has a single axis with 3 elements in it. Therefore, the shape of this array is 3. Next, the ndim method returns the number of array dimensions or the number of axes available in the array. In this case, a one-dimensional array has a single axis, so the dimensionality is equal to 1. Now, let's check higher dimensions. Now, in the case of a two-dimensional array, the shape method will result in a tuple with 2 elements. The first element, 2 in this case, represents the number of elements along the row axis or the 0 axis. Then, the second element, 3 in this case, in the resulting tuple represents the number of elements along the column axis or axis 1. Now, since this two-dimensional array has 2 axes, the ndim method will return value 2. Now, let's realize a 3-dimensional array. In this code example, we are creating a nested list of lists and converting it to a NumPy array. Variables a, b, and c are list of lists. Variable arr is a NumPy array of the nested list of lists a, b, and c. Each list of lists contains 2 lists, each of which has 4 elements. The 3D diagram visualizes the creation of this NumPy array. As you can see, each list of lists occupies its position in the 0 axis. Also, the elements of each list of lists occupies axes 1 and 2. Axis 1 represents the row axis, and axis 2 represents the column axis. Therefore, axis 0 has value of 3 since the array consists of 3 lists of lists. Axis 1 has value 2 since each list of lists has 2 rows, and axis 2 has value 4 since each list of lists has 4 columns. Lastly, the number of dimensions ndim is equal to 3 since the NumPy array has 3 axes. Another important array method is the size. The size of an array is the total number of values stored in it. The size of an array is just the multiplication of all values in the shape tuple of an array. Just like lists, NumPy arrays can also be indexed or sliced to extract certain values. It is important to note that the index number for each axis starts from 0 and increases along the axis, as per the length of each axis as shown in the figure. Now, let's look at the indexing technique. In array indexing, you can decide the depth of value extraction along the available axes in the NumPy array. For example, in the first option, slicing an array with a single index can be used with any array dimension. However, using two indices to extract certain values can only be used with two-dimensional array and higher. Using it with one-dimensional array will result in an error because the number of indices used is higher than the available axis numbers of the array. Next, using three indices to index an array can only be used with three-dimensional arrays and higher. Lastly, n number of indices can be used with n-dimensional arrays only, as using it with lower ones will result in an error. Note that array indexing always starts from axis 0, then axis 1, all the way up to the last specified axis. Alternatively, you can use this syntax for indexing and slicing by having a comma between index numbers instead of brackets for each one of them. Now, let's look at some examples. In this code example, variable arr1d is one-dimensional NumPy array of the list A. Since this array is a one-dimensional array, you only need a single index to access values within it. For example, to access first element, the index number will be 0. Also, to access the fourth value in the array, the index value will be 3. In the case of a two-dimensional array, you have the option to use a single index or two indices to access values in the array. Using a single index value will access the 0 axis of the array or the total row value. However, using two indices will access a specific value from within a row in the 0 axis from the array. Note that trying to use number of indices that is greater than the dimension of the array will result in an error. Now, let's look at array slicing techniques. In array slicing, you can slice rows or columns from a multi-dimensional array. Also, you can slice values from both rows and columns from a multi-dimensional array. Let's look at those scenarios. To start off, indexing a three-dimensional array requires 1, 2, or 3 indices. Using a single index, you will access the whole axis at the specified index 1. Adding one more index number will extract value from axis 1 that is a whole row. Adding one more index number will access the value in that row at the specified index. Now, as you might have noticed, indexing allows you to access each row while specifying a second index number in a three-dimensional array. The question is, how do you extract column values in an array? This is where slicing come in handy. This is the syntax to access a full column in an array. You have to use a colon instead of index 0 to extract all values in axis 0, then index 1 will dictate which column will extracted. The colon is not only used to extract a row from an array. In general, the colon takes full slice in the axis it is specified at. In the first example, a column was chosen since the colon was placed at a row axis or axis 0 in the case of a two-dimensional array. Values 4 and 7 were chosen from the array in the column index was specified at index 2. In the second example, the colon is specified at the column axis or axis 1 in the case of a two-dimensional array. This means that the full slice happens column-wise. Value 2.01, 6 and 7 were chosen since the row axis, or axis 0 in the case of a two-dimensional array, was specified at index 1. Notice that when we used a colon in the column axis in a two-dimensional array was the same as not having it in the first place. Therefore, you can choose a row in a two-dimensional array without having a colon specified at the column axis. Now let's look on how to column-wise slice a three-dimensional array. The row axis in a two-dimensional array happens to be at axis 0. However, the row axis in a three-dimensional array happens to be at axis 1. Therefore, to access a column in a three-dimensional array, the colon must be placed at index 1. For example, having a 0 value at index 0 and value 2 at index 2 will result in an array with values 3 and 7. Now, what if you want to choose those following values? How would you pick the axis indices? As you notice, those values are always consistent with their locations in axis 1 and axis 2. Therefore, index 1 and index 2 must have those values. However, the only variability is in axis 0. Those values span all over axis 0, so we need to use colon at index 0 to have full slice in it. This is the resulting array. Now, what if you want to choose those following values? How would you pick the axis indices? As you notice, those values span over all indices in axis 1 and axis 0. Therefore, index 0 and index 1 must have colon values. However, all those chosen values are consistent in axis 2 at position 0. Therefore, index 2 must have value 0. This is the resulting NumPy array. Now, let's look at a different slicing technique. What we have seen so far that a colon extracts values that span all over an axis. What if you want to get portions of values in each axis with a specific starting and ending indices? This syntax can do so. NumPy arrays follow the same rules as lists do. Slicing rules are similar to lists. Also, start values are inclusive, and end values are exclusive. Furthermore, unspecified end value along a certain axis means that array will extract all elements from start value to the end of the array in that axis. Lastly, unspecified start values along a certain axis means that value extraction will start from the beginning of the array to the end value specified in that axis. Let's take examples. In the first example, the 0 axis spans over indices 0 and 1. So the start index for the 0 axis is 0 and the end value is 2. Remember that the end value is exclusive, so value in the third row are excluded. However, the selected values span all over axis 1, so only a colon is used in for slicing axis 1. In the second example, the selected values span all over the 0 axis, so only colon is used for it. However, the selected values start from index 1 to the end of the array in axis 1. Therefore, the start index value is 1, and the end value is not specified so that array values are selected to the end of the array. In the last example, values in the 0 axis span over indices 0 and 1, and span over indices 1 and 2 in axis 1. Therefore, the 0 axis will have index value from 0 up to 2 which is exclusive, the index values from 1 to 3 which is exclusive in axis 1. Now, let's look at three-dimensional array cases. In this example, notice that the selected values span all over axis 0 and axis 1, so colon must be used as indices for those axes. However, the selected values only span over indices 0 and 1 in axis 2. Therefore, the starting index will be from 0 up to 2, which is exclusive. In the second example, notice that the selected values span all over axis 0, so colon must be used as an index for the 0 axis. Next, the selected values only span over a single row located at index 0 in axis 1, so the index value for axis 1 is 0. Lastly, the selected values start from index 1 to the end of the array in axis 2, so the required indices for axis 2 is starting value of 1 with no specified end value, in order to cover the selected values to the end of the array. Just like lists, dictionaries, and other data types, you can update a value in an array using this syntax. You will need the index of the old value to be replaced by a new value. However, you need to be careful when two variables are pointing to the same NumPy array. Just like lists and dictionaries, NumPy arrays suffer from the same aliasing issue, meaning that when two variables point to the same object, updating one variable will affect the other one that points to that same object. In this code example, notice the value of variable A before and after updating variable B. Previously, we visually understood how NumPy array work and how they are indexed and sliced. However, it is also important to comprehend how the visual representation of NumPy arrays are related to the bracket notations in a printed NumPy array. As you can see in the diagram, the NumPy array consists of three axes 0, 1, and 2, so it is a three-dimensional array. Axis 2 encompasses a row values, so each row is fitted within the blue brackets. Axis 1 encompasses multiple rows, so the red brackets encompasses multiple blue brackets. Lastly, axis 0 encompasses the groups of rows in the third dimension with the pink brackets. Understanding this brackets orders is crucial to understand the NumPy array reshaping. Array reshaping is the process by which you change the dimensionality of an array. For example, you can reshape a one-dimensional array into a two-dimensional array containing the same values in the original array. There are three rules when it comes to reshaping an array. First, the resulting size of the reshaped array must be the same as the original. Otherwise, the array cannot be reshaped and you will get an error. The second is that both original and reshaped arrays have the same element values. Lastly, elements are selected in row major order, left to right, top to bottom. Now, let's see how to implement this in Python. This is the syntax of the reshape method. Each input argument represents the length along each axis starting from axis 0 up to axis n. For example, in this code example, we are converting a one-dimensional array into 3 by 4 array. This means that the resulting array has 3 rows, each of which has 4 elements. Now, what if we want to change the same old array into three-dimensional array? Let's check another example. Here we are converting a one-dimensional array into 2 by 3 by 2 array. Therefore, axis 0 has length 2, axis 1 has length 3, and axis 2 has length 2. Notice that the size of the reshaped array is still equal to the original array. As we mentioned earlier, elements are reshaped in row major order, left to right, top to bottom starting from index 0 at the 0 axis up to the last index in the 0 axis, in the case of a three-dimensional array. Now let's look at another example. Now, what if we want to downgrade the dimensionality of an array from three-dimensional array into two-dimensional array? In this example, we are reshaping a 3 by 2 by 4 array into 8 by 3 array. As explained earlier, elements are reshaped in row major order, left to right, top to bottom starting from index 0 at the 0 axis up to the last index at the 0 axis. Look at this animation to see how it works. NumPy allows you to join a sequence of arrays along a specified and strictly existing axis. For example, concatenating one-dimensional arrays A and B along axis 0 results in a new one-dimensional array having the same values as A and B along axis 0. It is important to note that those arrays cannot be concatenated along axis 1 since both arrays A and B do not have axis 1. This is the syntax of the NumPy functionality of concatenation. The first input argument is a tuple of arrays that you wish to concatenate. The second input argument is the axis along which you want to concatenate those arrays. By default, axis value is set to 0, but you can set it to any axis value. Let's take another example. In this example, we have arrays A and B, each of which is a two-dimensional array. Since a two-dimensional array has axes 0 and 1, both A and B can be concatenated either along axis 0 or axis 1. When A and B are concatenated along axis 0, the concatenate function will concatenate A and B along the definition of 0 axis of a two-dimensional array. Therefore, both A and B will be concatenated row-wise. Similarly, when concatenating along axis 1, the concatenate function will concatenate both A and B according to location of axis 1 in the definition of a two-dimensional array. Therefore, both arrays A and B are concatenated column-wise. Now, how do you know if two arrays are compatible for concatenation along a specific axis? Let's see how it works. When having a two-dimensional array, you need to match the shape of all axes except for the specified one in the concatenate function. Meaning that, if you concatenate two arrays along axis 0, then the length in axis 1 in both arrays A and B must be equal. Similarly, if you concatenate two arrays along axis 1, then the length in axis 0 in both arrays A and B must be equal. Now, let's look at concatenation in three-dimensional arrays. In this example, we have two arrays A and B, each of which is a three-dimensional array. Concatenating A and B along axis 0 results in a new array as shown on the right. The new shape of the concatenated array is 4 by 2 by 4 instead of 2 by 2 by 4. When concatenating along axis 1 in a three-dimensional array, the arrays will be concatenated row-wise because axis 1 in a three-dimensional array represents the row of each subarray in the 0 axis. The new shape will be 2 by 4 by 4. When concatenating along axis 2 in a three-dimensional array, the elements will be added column-wise since axis 2 represents the columns in each subarray in the 0 axis. The new shape in this case will be 2, 2, and 8. When having a three-dimensional array, you need to match the shape of all axes except for the specified one in the concatenate function. meaning that, if you concatenate two arrays along axis 0, then the length in axis 1 in both arrays A and B must be equal, and the length in axis 2 in both arrays A and B must also be equal. Similarly, if you concatenate two arrays along axis 2, then the length in axis 0 in both arrays A and B must be equal, and the length in axis 1 in both arrays A and B must also be equal. Similarly, if you concatenate two arrays along axis 1, then the length in axis 0 in both arrays A and B must be equal, and the length in axis 2 in both arrays A and B must also be equal. It is important to note that the order of arrays defined in the concatenate function makes a clear difference in the output results. In the first case, you will concatenate B to A. However, in the second case, you will concatenate A to B. One final note on concatenation is that all arrays to be concatenated must have the same number of dimensions. As you can see in this code example, array A is two-dimensional and array B is one-dimensional. Although the number of elements in each row in arrays A and B is equal to 4, still they could not be concatenated since both have different number of dimensions. To solve this problem, one of the arrays must be reshaped in a way to match the dimension in the other one. Therefore, in order to concatenate array B to array A, array B must be reshaped to a two-dimensional array having only a single row. So to summarize, there are two rules for array concatenation in NumPy. The first is that the shape of all axes except for the specified one in the concatenate function must be equal. The second rule is that the number of dimensions in all arrays to be concatenated must be equal. NumPy allows you to join multiple arrays using not only concatenation method, but also the stacking method. One of the main differences between stack and concatenation is that the axis at which concatenation is applied must exist in all concatenated arrays. For example, you cannot concatenate it in axis 2 if all arrays to be concatenated are two-dimensional. However, stacking allows you to stack in an axis that not necessarily exist in all arrays to be stacked. Let's see how it works. As the name suggests, stack methods refers to stacking arrays upon each other at a specified axis. When stacking two or more arrays, the dimensionality of the stacked arrays will increase by 1. For example, stacking the one-dimensional arrays A and B will yield a two-dimensional array. Furthermore, the axis value that you assign in the stack method is the location of the axis of the resulting stacked array, not the original arrays. In other words, stacking happens at the axis in the result array along which the input arrays are stacked. For example, in the first case, stacking along axis 0 will allow you to stack the arrays along axis 0 where it is located in the resulting two-dimensional array. So arrays A and B are stacked horizontally. However, stacking arrays along axis 1 in the resulting two-dimensional arrays will vertically stack arrays A and B. Notice how values of each array A and B are rearranged vertically to match the specified stacking axis. Now, let's look at stacking two-dimensional arrays. Stacking two-dimensional arrays will result in a three-dimensional array. So the specified axis in the stacking method refers to the axis as defined in a three-dimensional array. In the first case, stacking along axis 0 as defined in the resulting three-dimensional array stacks arrays A and B depth-wise. In the second case, stacking along axis 1 as defined in the resulting three-dimensional arrays stacks arrays A and B row-wise. In the last case, stacking along axis 2 as defined in the resulting three-dimensional arrays stacks arrays A and B column-wise. NumPy allows you to do basic math operations on arrays. NumPy does mathematical operations element-wise, so for example, the first element in A will be added to first element in B, the second element in A will be added to second element in B, and so on. Now, what if array B has shape 1 while array A has shape of 4? In this case, array B will expand itself with the same value to match the shape of array A, then, mathematical operations can be done element-wise. Array B expansion to match the shape of array A is called array broadcasting. NumPy does not do this expansion as it is not efficient, but this is the analogy it follows. There are two rules for array broadcasting in NumPy. The first is to check if the dimensions are compatible for expansion moving backward from the last dimension in each array. The second rule is that dimensions are compatible for expansion provided they are equal or one of them is 1. Let's see an example. In this example, array A has shape 2 by 3 while array B has shape 3 only. Both arrays A and B are compatible in the last dimension since they are equal, while the first axis of B must be expanded to match that of array A, therefore, array B has new shape of 2 by 3. Then element-wise math operations can be done. Now, in this example, array A has shape 2 by 3 while array B has shape 2 only. Arrays A and B are not compatible in the last dimension since they are not equal nor one of them is 1. Therefore math operations cannot be done. The same concept can also be applied to three-dimensional arrays.